Now, term-by-term differentiation of Fourier series and term-by-term integration is actually rather interesting. So this is now two properties which we actually will use in our calculations. So I do them in a bit more detail. Before I go here to theorem 2.8, allow me just to open another empty page. So here I write down the general Fourier series again with the coefficients a0, an, bn, and then the cosine n pi x over L and the sine n pi x over L. And let's make life simple, and I choose L to be equal to pi. Okay. If I do this, then in this cosine here, the pi cancels, and in the sine, the pi cancels. And then I look at the function, let's maybe call this g, maybe 3 cosine of 2x plus 5 sine of 7x. So what happened? Well, I've chosen only two terms. I've chosen one cosine term and one sine term. And the cosine term is of the form cosine nx, okay, where in this case n is 2. And so then the coefficient for the index 2 would be 3. So this means the coefficient a2 is equal to 3. For the sine term, the sine is also of the form sine nx, right? But now n is 7. And the coefficient, which would be the b7, is now 5. Okay. So this function g is now also a Fourier series. We still call this a Fourier series, although it has only two terms. But what we can do now is I can differentiate this. I can do g prime. Okay. So differentiating cosine, this is minus sine, and then the inner derivative 2. So this is minus 6 sine of 2x. If I differentiate sine, I get the cosine. Inner derivative is 7 plus 35 cosine of 7x. And now you see, this again is the sum of sine and cosine terms. And here the sine index now is the index 2, and the cosine index would be the index 7. But still, this is, again, a Fourier series. Isn't that cool? And similar for integration. Right, what we also can do, we can integrate, let's say, from 0 to x, the function g. Let's call this integration variable now y. So then integrating cosine gives us sine, inner derivative is a 2. And then here integrating sine is minus cosine, so then we have 5/7, inner derivative is 7 cosine of 7x, evaluated between 0 and x. So then we sub it in. First we sub in the x, so we have 3/2 sine of 2x minus 5/7 cosine of 7x. And then we sub in the 0. Sine at 0 is 0, but cosine is not. And we get minus and minus, which is plus, so plus 5/7. Cosine at 0 is equal to 1. So this is also a Fourier series. Yoo-hoo, isn't that cool? The only thing is here we get this a0 term, which we didn't have in the original one. But you remember, if you do antiderivatives, you get an additional constant, right? And so here the constant would be 5/7. Still, this is a Fourier series. So having one Fourier series, you can differentiate, you get another one, or you can integrate and you also get a Fourier series. So that's pretty cool. And this will be the contents of our next, I think, 2 or 3 theorems. So here's the result for the term-by-term differentiation of Fourier series. And this all works, like I explained in the little example there, if we don't have jumps. On jumps, we cannot necessarily differentiate a Fourier series, but if we don't have jumps, we can. And so that's what we say here. So f has to be continuous, but then also kind of continuous at the limits, minus pi and pi, or minus L and L. So in the general case, we would say f of minus L has to be equal to f of L. Right, so if you do the periodic extension, that you don't create jumps at the periodic extension points. But then also we want the derivative to be piecewise smooth on this interval from minus pi to pi. And then the Fourier series is differentiable. That's what's coming now in this complicated sentence. So the Fourier series representation, where the coefficients are given by the integrals, which we know so well, is differentiable. So here is the statement. Is differentiable, and we can differentiate term by term. Okay, and if you differentiate the cosine term, you get minus sine. This happened right here with an inner derivative n. If you differentiate the sine term, you get cosine, which happened here with the inner derivative n. Okay, so then this is the Fourier series of the differentiated function f prime. That's it. So essence here is you can differentiate Fourier series as long as you're not differentiating on a jump. So it's similar for the cosine series, but remember, for the cosine series we had functions defined only in the positive. So let's say from 0 to L, or here from 0 to pi. And then we can do even or odd extensions to the negative bit, and this is a way to get the cosine series for the even extension and the sine series for the odd extension. So here's the cosine series, and then again you can differentiate if you know that f prime is piecewise smooth. If you differentiate cosine, you get sine with a minus sign, which I put in the very front, and the factor n in front, and then this is a new Fourier series for the derivative. And guess what? Same result for the sine series. However, here we have this condition that we don't create a jump if we do the odd extension at 0. So f at 0 has to be f at pi, has to be equal to 0. That was a condition we didn't need for the cosine series, but we do need it for the sine series to be able to differentiate. And so then if we differentiate sine, we get cos, and then we get the factor n from the inner derivative. The essence is you can do everything just fine if you don't have jumps. So let me give you one more, which is about term by term integration. Term by term integration needs less conditions. You only need f to be piecewise continuous. You don't need a condition on f prime, because now we integrate, right? We don't differentiate, we integrate. Otherwise, we can do it term by term, which is then shown here on the next page. So f has a Fourier series given here. And then if we integrate this from minus pi, so which is the lower limit, to some point x up here, we can integrate the cosine. We get sine with the factor 1 over n. We can integrate the sine, which gives a cosine with the factor 1 over n. But then also from the lower limit, we get this additional term, like you saw in my little example where I had like 5/7 as an additional term. So this comes from the lower boundary minus pi. In this case, turned out to be minus 1 to the n plus 1, and then divided by n. Note here that this is not directly a Fourier series because of this a0 times x term. So there's a linear dependent on x, and we would need to find the Fourier series of x and put it there. And we did this, right? This was the formula minus 1 to the n plus 1 divided by 2n minus 1 sine of nx. So this kind of formula would have to actually be used in the very first term to make this a real Fourier series.